Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be examining the axiomatic approach to probability. It's one of the four approaches to probability that I mentioned to you in an earlier video. So let's remind ourselves a little bit about the axiomatic approach. First of all, the axiomatic approach is the most rigorous. There's very little approximation involved. It will allow us to use all of our mathematical tools that you've learned, calculus, algebra, geometry in some cases. It will also allow us to use set theory and set theory notation that we examined a bit earlier. The axiomatic approach to probability does not begin by defining what probability is. Instead, we discuss the properties that probability must obey. So let me write that down. We don't define what probability is, but rather we describe or begin by examining the properties that probability must obey. And the axiomatic approach to probability is good for just about every manner of chance experiment. It's good for chance experiments that have finite or infinite number of elements. Have a finite or infinite of elements, or more commonly referred to as outcomes. And these outcomes can be either continuous or discrete. They can be finite or infinite. So, the axiomatic approach to probability is good for chance experiments that have either a finite or infinite number of elements or outcomes, and these outcomes themselves may be either continuous or discrete. It covers a lot of territory. Well, the axioms are and there are only three. First axiom. The probability of any event A lies somewhere between 0% and 100%. All right? I can't have a probability less than 0, and I can't have a probability greater than 1. Probability is a real number in fact, that lies between 0 and 1. The second axiom is the probability that the sample space equals exactly 1. And remember, S is sample space. All right? This is the event that has all possible outcomes. It's the event containing all possible outcomes. And remember that an event occurs if we perform a chance experiment and one or more of the outcomes in the event occurs. The sample space contains all of the possible outcomes. For sure, 100% likely, if we perform a chance experiment, something's going to happen. One of the outcomes in the sample space is going to occur. It's 100% likely that that will happen. Therefore, the probability of the sample space is always exactly 1. Here's the third axiom. The probability of A union B equals the probability of A plus the probability of B if A intersect B equals the empty set. That is, this means that A and B are disjoint. That's a new term I want to introduce. Disjoint means that two sets or two events, A and B, have no intersecting elements. So from a Venn diagram approach, if this is my sample space, over here is event A, over here is event B, and as I've drawn them, they have no intersecting elements. They're completely disjoint. That's what two disjoint sets look like. That's it. There are only 3 axioms of probability. Everything else that we do that's probability related for the rest of the semester can ultimately be derived from this perspective. These axioms cannot be proven. That's the nature of something that's axiomatic. It's fundamental. It can't be proven from something more fundamental. It's just something that we can reason out logically and make sense of. Everything else builds from here. So let's start looking at some derived probability relationships. And we'll do this through a series of examples, and the results of each of the examples can be used in additional examples later on, so the probability relationships that we derive can become ever more increasingly complex. So let's start off with something simple. One. First of all, recall that the sample space intersects the empty set at the empty set, meaning that the set containing everything intersects the set containing nothing exactly nowhere. Sample space intersects the empty set at the empty set. Moreover, the sample space union the empty set equals the sample space. Meaning, if I add everything to nothing, I get everything back. All right? Anything plus 0 equals the initial anything. All right, these two statements here are statements of set theory. I haven't introduced any probability at this point. Now let's introduce some probability theory. Probability of sample space union the empty set, since they're disjoint, they don't intersect anywhere, is the probability of sample space plus the probability of the empty set. All right? That is the third axiom. All right? The sample space and the empty set intersect each other nowhere. All right? Sample space and the empty set are disjoint. They have no intersecting elements. All right? But from my relationship over here, from this one right here, I know that sample space union the empty set equals the sample space, so I can also write that this equals the probability of the sample space. All right. Rewriting my last two steps, I can say the probability of the sample space equals probability of the sample space plus probability of the empty set. The probability of the sample space is exactly 1. And this is the second axiom. And therefore, canceling 1 from both sides, I can find that the probability of the empty set equals 0. All right? Probability of the empty set equals 0. Now, most of you would say, well, that's obvious. That's axiomatic. Actually, it's not. It's something we derived. We could have either said that when we were writing down the axioms earlier, we could have said that the probability of the sample space equals 1, or we could have said the probability of the empty set is 0. One of those two is axiomatic. The other one is derived. Typically, we assume that the probability of the sample space being 1 is the axiom. All right? But we came to a logical conclusion. You'll notice that these last several steps are probability theory. All right? We used set theory to start with, and then we applied probability theory. Don't confuse set theory with probability theory. They are not the same. Let's do another example. First, notice that A intersect not A equals the empty set. That means that A and A not, or A complement, are disjoint. Let's try that again. A and A complement are disjoint. Moreover, A union A not has to equal the sample space. All right? These two steps here are come from set theory. A intersect everything that's not in A has to be the empty set. A union with everything that's not in A has to equal the sample space. All right. So now let's apply some probability theory. Probability of A union not A equals the probability of the sample space, and that's because of this relationship. And by the third axiom, I can say that this is the probability of A plus probability of not A. And I get to this point by the third axiom. All right. By the second axiom, I know that the probability of the sample space is exactly 1. So I can write 1 equals the probability of A plus probability of A not. And here, to get to this step, I have employed the second axiom to get to that point. The probability of the sample space equals 1. So I can rearrange one more time, and I can find that the probability of event A naught or A complement equals 1 minus the probability of A. So we have derived something, once again, that might seem rather obvious to you at first glance. The probability of A not occurring, equals 100% minus the probability that A actually occurs. All right, again, that might seem rather obvious, but that relationship is not axiomatic. It's derived. All right. Let's go a little deeper. Third, what happens if we have two events that are not disjoint? How do we find probability relationships related to those two sets? So what if A and B are not disjoint? That is, that they share elements. Not disjoint means A and B share elements. Or outcomes. So from a Venn diagram approach, if this is my sample space and this is event A, event B might look like this. So we'll call this event A, and this will be event B. Okay? All right. And by the way, I ought to mention that this is an extraordinarily important example. This is something you might see again in your future on tests. I strongly suggest that you study and know how to reproduce all the steps that I'm about to show you. All right? So let's peel this apart. Let's do this in a couple of different steps. 1. Let's do some set theory first. A union B, let's just write down a true statement to start with, is A union B intersecting the sample space. A union B, any event can be written as the intersection of that event and the sample space. Any event intersects the sample space at itself. That's what that means. All right. The sample space can be written as the union of any event and its complement. The sample space can be written as any event, A, for example, union with everything that's not in A. Then we're going to apply the distributive property, and we'll get this far. A union B intersect A naught. So this is distributive property. All right. Notice that A and B intersect A naught are disjoint. A and B intersect A naught are disjoint. They're disjoint. A and B intersect not A are disjoint. So let's look at that over here. Let me outline event A in red. All right, that's event A. And B intersect A naught is this area here. All right. Event A and B intersect A naught are disjoint. All right, so let's write down something else that's true. B, event B can be written as B intersect A union B intersect not A. Any event can be written as the intersection with another event and the intersection with the complement of that event. And another thing is B intersect A and B intersect not A are disjoint. So B intersect A and B intersect not A are disjoint events. Okay? All right. So this is as far as we can go with purely set theory. Everything I've written on the board so far is all set. Everything I've written on the board so far is simply set theory. Let's apply some probability theory. All right. Remember earlier we had this. We had this statement. We had A union B equals A union B intersect not A, and A and B intersect not A were disjoint. From the third axiom, we can write this down. This is by application of the third axiom. Okay? Moreover, we had this as a true statement at the end of the last board. We have that B equals B intersect A union B intersect not A. And those two intersect, the union of these two events, B intersect A and B intersect not A, are also disjoint. So applying the third axiom of probability, once again, we get that the probability of B equals probability of B intersect A plus probability of B intersect not A. Once again, application of the third axiom. Now I'm going to rearrange this last step. I'm going to rearrange to get probability of B intersect not A equals probability of B minus the probability of B intersect A. And then I'm going to take this last relationship and I'm going to plug it back up into here, rearrange and simplify, and what I get is that the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. That's my result that I'm going after. All right? If A and B are disjoint, then the probability of A union B is just the probability of A plus the probability of B. But if they share some common elements, meaning that A and B are not disjoint, then I have to subtract off the intersection. Let's take a look at that from a Venn diagram perspective. And this is my sample space. All right. The probability of A is more or less represented by this red hatched area. And the probability of B is more or less represented by this green hatched area. And you'll notice that the green hatched area and the red hatched area have some overlapping in this region. Right? That is A intersect B. That's a B. All right? So my relationship is that the probability of A union B equals probability of A plus the probability of B minus the probability of A intersect B. In effect, if I just add the probability of A and the probability of B, I double count the intersection. Just adding probability of A and the probability of B together, I double count. I'm double counting the probability of the intersection, so I subtract it off once there. That's what that's all about. Okay? So once again, you should spend some time studying this example. It's a very important example. This relationship up here is something we will use very often throughout the semester. You ought to know where it comes from. All right. Let's do some more examples. What we're going to do is we're going to toss two fair coins and observe heads or tails up. I'll toss two coins and I'm going to observe heads and tails. 4 possible outcomes. And they're all equally likely. Because I'm assuming that the coins are fair. So this will, in effect, be an application of the equally likely outcomes approach to probability. All right, so let's write down one event. A1 is heads 1, head 2, heads 1, tail 2, heads 2, tail 1. This is the event that at least one head is up. At least one head is up. By application of the equally likely outcomes approach to probability, the probability of A1 is 3 chances out of 4. There's 4 possible outcomes. A1 has 3 outcomes, so the probability of A1 is 3 chances out of 4, 75%. Event A2 will be heads 1, heads 2, tail 1, tail 2. This is the event that the coins are the same. Clearly, the probability of A2 equals a half. What is the probability of the union? They intersect here. They intersect where the events A1 and A2 intersect where both coins show heads up. So we can apply the relationship that we derived previously. Let me block off some space here while I do this. The probability of A1 union A2 equals probability of A1 plus probability of A2 minus the probability of A1 intersect A2. Probability of A1 is 0.75. The probability of A2 is 1/2. And the probability of the intersection, they intersect at only one element. Probability of A1 intersect A2 is 1/4. They intersect at only one element. So I subtract off 1/4. And I add that all up, and I get 1. Why is that? Well, clearly, if we look at this and spend a little time with it, we see that A1 union A2 equals the sample space. A1 union A2 covers all possible outcomes. Heads 1, head 2, head 1, tail 2, tail 1, head 2, tail 1, tail 2. All 4 possible outcomes. The probability of the sample space is always 1 by application of the second axiom of probability. So it all works out. All right. Let's do another example. Let's say we have 2 events, A and B, and we know that the probability of event A is 90%, and we know that the probability of B equals 80%. And what I want to know is, what can I determine about the probability of the intersection? What's the probability of the intersection? All right. Probability of A union B equals probability of A plus probability of B minus the probability of the intersection. I can't be sure that events A and B have no intersecting elements. Therefore, I'm going to start with this relationship. All right. I know that the probability of A is 0.9, Probability of B is 0.8. This gives me 1.7 minus probability of A intersect B. Okay, but I know this from the first axiom of probability. 0 has to lie between probability of A union, probability of A union B has to lie between 0 and 1. That's the first axiom. That's the first axiom. All right. All right, that gets me that far. My first axiom tells me that the probability of A union B, my initial statement up here, has to be between 0 and 1. Plug in my relationship for the probability of A union B, which simplified is 1.7 minus the probability of the intersection, and then do some algebraic manipulations. I find that the probability of A intersect B has to be greater than 70%. But, and this is an important but, the probability of the intersection can never be larger than the probability of the least likely event. Probability all right? The probability of the intersection can never be larger than the probability of the least likely event. Probability of the intersection can never be larger than the probability of the least likely event, which means that 0.7 is larger than probability of A intersect B, and that's got to be less than 0.8. The least likely event is event B. It has a probability of 0.8, and by the previous manipulations we see that probability of A intersect B has got to be greater than 0.7. And I see an error in what I've written over here on the right-hand side. The probability of the intersection can never be larger than the probability of the least likely event. Okay? All right. Let's just do one last example and call it a day. What if probability of A is 0.9, probability of B equals 0.8, and the probability of the intersection equals 0.75, right in the middle. Let's find three different probabilities. The simple one is probability of A union B is probability of A plus probability of B minus the probability of the intersection. Very simply, that's 0.9 plus 0.8 minus 0.75, and that is 0.95. That's an easy one. Let's do something a little bit more complex. What about the probability of A intersect B naught? Well, let's write down some true statements. The probability of A equals the probability of A intersect B plus the probability of A intersect B naught. This is true for any two events. This is a general true statement. A intersect B is disjoint to A intersect not B. If I find the probability of that intersection and that intersection, add them together, I have to have the probability of A. That's a true statement for any two events. All right. Rearrange this a bit, and I get probability of A intersect B naught equals probability of A minus probability of A intersect B. All right. And this is 0.9 minus 0.75, and that's 15%. From a Venn diagram approach, we can examine this example. There's my sample space. Here's event A, and over here is event B. This is this region here. All this hatched area here is A intersect not B. A intersect not B. Probability of that event is 15% in this example. Got one more piece to this example. Let's take on the next page. We'll look at part C. And I want to find the probability of A naught intersect B naught. And to do that, I'm going to use De Morgan's theorem. Probability of A naught intersect probability of B naught equals probability of A union B complement. This is De Morgan's theorem. And this can be written as 1 minus the probability of A union B. Remember earlier we saw that probability of A equals 1 minus probability of A complement. That was one of our early derived probability relationships, and I'm applying that here in part C of this particular example. From the previous page, we saw that the probability of the union was 95%. So part C is 5%. That's the result. All right. That's all I have for today. That's our initial examination of axiomatic probability, some derived probability relationships, and how they kind of build upon one another to get more and more complex probability relationships. Please examine what you've learned very carefully, and if you have any questions, please do contact me at your earliest convenience, and I'll do everything I can to clarify any misunderstandings. Have a nice day. Bye-bye.